Now we should be good. Okay. Hello, everybody. Thanks for being here tonight. So the goal with this session, normally what I do is like a quick fire 1 hour review 2 nights before the exam, because tomorrow night I want you sleeping, right? Like you have an 8 a.m. exam. Those are the hardest ones to have. And I want to make sure that we're doing this 2 nights ahead so you can still sleep tomorrow. Hello, everyone. Thank you for being here. Yes. And I'm getting some questions. Can we cover the FRQ with titration graphs? You got it. Like that is the plan for tonight. This is geared. I have this ridiculously long slideshow, which is why I am starting so late. Not because I want to go through all of it, because I'm going to link this in the notes right after I get off so that you guys have access to all of the content that you need. And then you can just like flip back and forth between the units. I'll show you how it all works out. But let's just go ahead and jump right in. As we're doing this, I am watching the chat. I'm going to try to keep up with it. I know there are a lot of you here tonight. Thank you all for being here. So what I'm going to do is I'm just going to try to answer those questions. I'll stop at different points, hop in the chat, see what I've missed, and keep going from there. All right? All right. It might be chaotic, but that's okay. It's AP season, like it is just chaos. So if you want to drop your state where you're coming from, I'm seeing a lot of like different students, different classes being mentioned. Maybe we'll do a few shout outs. Yes, I will save it. And a lot of times what I'll do is if the live is chaotic, I'll record a video right after too, so that you can just go through it. I don't like to waste time. You guys don't have a lot of time. So my goal is always to make all of my content as succinct as possible. All right, so let's keep rolling. So what I want to do is we're going to focus on the big ideas. I really want to make sure you're getting some active practice. And yes, you're going to have access to all of this, all of the notes. There's also a free problem set that I just wrote based on my FRQ predictions for this year's test. I just want you to feel confident going into Tuesday's exam. You are ready for this. You really are. And I'm seeing a bunch of states coming in. Yes. All right. I'm seeing someone else. I'm in Virginia. So I'm right outside where the University of Virginia is. That's where I'm coming from. Looks like we are all over the place. Sorry, I know it's late. I have 3 little kids, so I try to do things after they go to bed. All right, let's keep going. So these are the big ideas. Yes, it did just start. Sorry, I'm a little bit behind. All right, so these are the big ideas and the big buzz phrases that I'm just going to review, because sometimes like there are certain things that you may have missed in class and all of a sudden they click and you're like, what? How did I not know this? But this is the time for things like this to click, right? So let's go ahead and keep moving through. So the first one is effective nuclear charge. Like, what is that, right? ZF, right, is what a lot of students will tell me, like, oh, I know ZF. Like, okay, explain it, right? This is what all of the periodic trends tie back to. So this is really what I want to focus on with this, is understanding, like, do you recognize that the reason the atomic radius shrinks as we moved left to right across the period is because we're adding protons to that nucleus. The more protons we have, the higher the magnitude of that positive charge. Think about a magnet, right? The stronger that magnet is, the more those electrons are going to be attracted inward. That's what effective nuclear charge is. That's what's going to drive Coulombic attraction. That's what's going to drive all those periodic trends. So I don't want you justifying anything with just arrows or anything like that. I want you coming back to this idea of effective nuclear charge. So the greater the effective nuclear charge, the smaller the atomic radius, because the more those electrons are attracted towards the nucleus. The closer they are, the stronger the Coulombic attraction, and therefore the more energy it's going to take to remove them. And that's why we have a higher ionization energy. So just keep in mind, all of those trends tie back into that. All right, let's keep rolling. So the next one is Coulomb's law. So the joke is, if you want a 5 on Tuesday's exam, you just have to mention Coulombic attraction as much as possible, right? Not quite the case, but you are going to see it like everywhere, right? So what we want to do is we want to look at the at your equation sheet. If you have not printed this out, it is not too late to print it out now and start looking at it, because time is money on this exam. This exam, the hardest part oftentimes is just dealing with those time constraints. So if you can print out this formula sheet or just look at it on your phone and get really familiar with where you find everything, that's also going to save you. So Coulomb's law, just this idea that the force, the electrostatic force, why do we have to have so many different complicated ways to refer to everything in chemistry, right? So an electrostatic force, that's either going to be an attractive or repulsive force between 2 charged particles. Think about a magnet again, right? So the larger the magnitude of charge, so if I have an ion that's +2 versus an ion that's +1, the +2 one has a bigger pull on other particles, right? And then the distance between charges also matters. So the shorter the distance between charges, the stronger those attractive forces or repulsive forces are going to be. So just thinking back to how we relate all of this, and we'll go through like an example with this so you see how we actually relate this. Oh, hello, AP Bio Penguins. Thanks for stopping in. Yes, so good news is you get both a paper equation sheet and a paper copy of the periodic table. Make sure you give last year's students, you rub it in their faces right now. Don't do that. It was miserable that they didn't have it last year, but I'm so glad that you guys do. So you'll have that. You'll have scratch paper. With the hybrid exam, I didn't spend any time on that, but the hybrid exam, all of your MCQs are going to be on the computer. And then when you sit down to take your FRQs, you'll have an FRQ booklet. So if you have a question where, let's say, you have to draw in a graph, they'll give you the graph to work with. You're not going to be drawing that from scratch. So your FRQ booklet is going to have certain things. You'll see particle diagrams in there, things like that, like the basis of certain questions. Also, don't get stressed out. There are different versions of the FRQs in your booklet. It's going to say, okay, put your answer to version A here, right? If you happen to put your response in the wrong spot, don't crash out over that. Don't start erasing everything and moving it. Keep it right there. The readers are going to search through that booklet. They're going to find that question. Don't waste time, okay? Yes, you want to try to make sure you're using the correct spot for the correct version, but if you find yourself, you're at part F of a long FRQ and you're like, oh, I put this in the wrong spot. Don't waste time, okay? Don't waste time. All right, so let's keep moving. So this is just relating back. So just relating effective nuclear charge and Coulombic attraction. Again, this just shows how it all ties together. All right, let's just keep going. So the other big thing you need to be really familiar with is Q versus K. And at this point, I think a lot of students have spent a lot of time on equilibrium lately, but maybe you've forgotten what Q is. Q is calculated in the exact same way that K is, right? It's the concentration of the products over the concentration of the reactants raised to the power of those exponents. If we're looking at the pressure, right, it's the pressure of the products or the pressure of the reactants. It's actually really simple to do that, right? But then what do we do, right? Why do we care about this? Well, Q, the reaction quotient, is going to tell me what that relationship is at any point other than equilibrium. Okay, so what we are going to be doing is we're going to be comparing Q to K to kind of see what needs to happen or what is happening in that reaction as we move towards equilibrium. So I would just have these memorized. So if Q is greater than K, the reverse reaction is favored. It's really important with QSP. We will do something with that in just a second. If Q is less than K, forward's favored. If Q is equal to K, we are at equilibrium, right? And then when it comes to equilibrium, you can look at the screen. If the K is greater than 1, we're favoring the products or the forward reaction. Less than 1, we're favoring the reverse reaction. All right, let me hop on and see what's in the chat. Should we use pen or pencil for the FRQ booklet? That is up to you, right? A lot of teachers will say bring both, whatever you are comfortable with. If you are using pencil, make sure you're writing nice and darkly. But yeah, you should be fine. Just do not use an erasable pen. Erasable pens, I don't know if you know this, a little bit of chem here. A lot of those are going to be erased with temperature. So let's say your booklet is placed in a spot where it's hot. All of a sudden, all of your writing is gone. Okay, so just be careful with that. All right, and our FRQ is going to be in order on the computer. Yeah, you're going to have all of your FRQs. You can skip around. You don't have to go one by one. And I actually recommend a 3-pass system with these tests, right? Like go through, answer all the easy ones first. Flag them. You can use Blue Book or use your scratch paper to keep track of the ones that you know are going to take some time and the ones that you have no idea how to handle. Then go back to those. So I do not recommend taking the test in order. When I sit down to take it, when it's released on Thursday, because I'm such a nerd that's what I look forward to doing, I will be skipping around, right? And I've been doing this for a long time. There's no penalty for skipping around. Yeah. All right, let me see. Yeah, do we need to show, you do need to show your work on your actual booklet, not on your scratch paper. Your scratch paper will be turned in, but that doesn't mean it's going to stay with your actual answers. So you do want to show your work. And there are, if you do not show your work, even for a simple subtraction, you don't get the points for it. So make sure you are taking the time to show your work. You don't necessarily have to include units with that work. However, it does help to have that in there. As a reader, they're going to be looking for signs that you know what you're doing, right? They're going to read, your answer is going to be based on the last thing that you write. You can draw a box around it if you want to, if it makes you feel better. But it does always help to have your work on there. Yeah. All right, yes, AP Bio Penguins is reminding everyone, no erasable pens, yes. All right, so let's keep moving forward. I just wanna get through these big ideas, and then I promise we're gonna just practice. And if you have not downloaded the practice problems, I decided at 11 o'clock last night that I was gonna make a new problem set for you all based on my FRQ predictions. So if you look, you will see that it says download the new problem set. Download that so you have it, and we'll just run through those tonight as well. All right, so thermodynamically favored conditions. You just got to know these, right? Have this memorized. If you don't have it memorized yet, you still have time, right? Between now and Tuesday. Because basically, you're going to have questions where you have to justify whether something is driven by enthalpy or entropy, or whether a student is right in saying, oh, with a negative enthalpy and a negative entropy, this is always thermodynamically favored, TDF. No, not. It's not. That's not true. So, just make sure you feel really comfortable with these, and we're gonna go back into all of these. Yeah, and okay, so I'm just gonna go ahead and answer some of these other questions. We are absolutely gonna practice with FRQs. Calculators do not need to be cleared. That does not mean I'm recommending that you hide a bunch of notes in there. You don't have time for that. Like, just don't even try to do something like that. Your calculators do not have to be cleared, though, so you don't have to be stressed out about losing stuff for other classes and whatnot. You are gonna get a paper copy of the periodic table and the equation sheet. So you'll have that. You'll also have scratch paper. So you'll have that, you'll have your FRQ booklet, you'll have all of those tools. So that's really nice. I'm sure you've heard last year that was not the case. So I'm really glad that they changed their policy this year. All right, so let's see. This was just a TDF. Yeah, we're gonna skip this. I want to get into the FRQ practice. And like I said, I'm gonna attach all of these. I will link all of these right after I get off so that you have all of this. Let's see. See, this is not related to what this is how these sessions work. So I have so much content in this ready to go, but I want to just kind of respond to what you all are asking for. And yeah, here's a great question. So can we use symbols like up arrows or down arrows instead of writing out increased or decreased? You can. Yes. Save your hand muscles for all of your DBQs and things like that for you have on your other AP exams. So as long as readers, we'll get into like all of this, but as long as readers know what you are saying, and same with abbreviations, really common abbreviations are fine. I do recommend like using the full term, like for example, thermodynamic favorability, parentheses TDF. And if you do that, then you can use TDF through the remainder of that question. Between questions, though, you're not going to have, you can't assume that you're going to have the same reader for each question, right? Each test is graded on a question by question basis. So if you justify or if you explain, I don't know what I'm saying. If you use an abbreviation, you can only use it in that one question. Yeah. All right. And tips. Yeah, the problem sets are actually linked in the video notes. So if you look at the description of this live right now, you will see it says like download the new FRQ problem set. That's where you can get those. So go ahead and do that. Yeah. How do we format the paragraphs we write? You know, what the goal in chemistry is to be as succinct as possible, right? We don't need an essay. 2 to 3 sentences is typically enough to answer any of these FRQs. Yeah. Thanks for being here, AP Bio Penguins. Yes, you would have to redefine any abbreviations at the start of each subpart. So if you're not at the start of each subpart, at the start of each FRQ. So every time you see a new FRQ, that's where you have to give those abbreviations again. Yeah, and what's the best way to maximize points on the FRQ if you don't know a question on there? There are going to be questions that you don't know. You're going to sit down, you're going to be like, whoa, I have never seen any of this before. What I recommend doing is skipping to the next FRQ and then going back to that one. As you're doing an FRQ, if you have no idea how to do parts A through C, but you know how to do part D, add in, okay, assuming 5.27 moles, and then go from there. You can still get full credit using that incorrect answer if you know how to show your work on the rest of it. So I'm really a big fan of like taking that first pass to answer all the easy ones and going back and using the test to your advantage. Sometimes as you're going through an easier FRQ, all of a sudden something clicks and you're like, oh wait, I know how to do that one. So you can go back and do that. All right, let's see. I had another question. I have a lot of questions coming in. You guys are great tonight. Can I write in bullet points? Yes, you actually could. You don't have to write in complete sentences. I mean, I think a lot of teachers will tell you, like, don't waste your time. Watch, I'm going to get in trouble for this, but yeah, don't waste your time writing out complete sentences. This is a chemistry test, right? We care about chemistry. Yeah. Is there a lot on IMF? So IMF is part of Unit 3, which is weighted the most heavily out of all of the units. That's 18 to 22% of the entire exam. So I do recommend really knowing IMF pretty well and just making sure that you are, yeah. And someone was asking about LDF. LDF is London dispersion forces. Everything experiences London dispersion forces. Yeah, okay. Let's see. Sorry, I have so many questions coming in. This is awesome. Yeah, if you show, okay, I'm going to show this one. If you show your work, do you have to verbally explain your answer? It depends. So a lot of times, if you look at previous scoring guides, there will be times where we'll have two options, right? You either could have shown your work, you could have mathematically shown your work, or you can describe it. So if you want to do both, it's always a little bit better, right? You have a better chance of getting those points. Yeah, so here's another question about just the format of the test. Are the FRQ questions on Blue Book or on the booklet? So the actual questions are going to be on Blue Book on your screen. However, in your booklet, you are going to have certain things that are printed out. So whether that's like a graph that you then have to interpret, or a particle diagram that you're working with, and you're then creating a new particle diagram to match that, you'll have things like that. All right, let's see. Yeah, okay. So someone asked if I got around 70% of an FRQ, is that bad? So keep in mind, to get a 5, it changes every year, but about a 74 to 76% should be all that you need to get that coveted 5. Yeah, okay, I have a lot of questions here. I'm putting all these, I promise I'm getting these in my head right now so that I can go through a lot of that. Yeah, are there different versions of the FRQs? Yes, there are. There are several versions of FRQs. If you look at the booklet, it should specify where you put your answers. If you accidentally put your answer in the wrong spot, don't crash out over that, okay? Take a breath, write a note to the reader at the top, and don't worry about transferring it. They will find your work in that booklet. Do we need to know lab procedures? Yes, but typically what happens is the lab procedures, you are going to be just, you'll be filling in steps, like missing steps in a lab procedure. And typically we see something like creating a solution, right? You put the solid in the empty, oh, look at this, empty volumetric flask. Then you add deionized or distilled water until you get exactly to this marking. You carefully invert it. You move it back and forth, right? Invert it until the solid dissolves. Just something like that. And you're filling in like one or two of those steps. And that's what we typically see. All right. And if you were to do the FRQ practice set with a time limit, how many minutes would you recommend? Yeah. So when you think about the long versus the short FRQs, you want to make sure that you're spending about 22 minutes on the long FRQs, and the short ones are going to be about 10 minutes. So just learning how to practice, there is going to be like some leeway with that. It depends, right? You have your total amount of time for the exam, give and take. Sometimes those long FRQs, if you feel really confident with them, you're going to fly through those. So it just kind of depends. If you are still looking for some practice, like right before, I would say like look at the 2025 released FRQs and go from there. Try those out, time yourself, how much time you're supposed to have, and then kind of see how you go from sorry, let me rephrase that. So sit down, try out those FRQs, watch the time, feel that pressure, and then take a minute, just step away, get some water, and then start looking at the scoring guides and seeing what you missed and seeing what they're looking for. All right, I am going to keep moving, and I'm just going to keep going. Yeah, key features on our calculator, digital calculator. So calculator, you need to know where the log function is, the natural log, things like that. Those are the things you want to look for ahead of the exam so that you feel, yeah. All right, let's keep moving forward. So those were the big ideas. And let's see. I guess let me go back into, I've had this on the screen, but haven't actually talked about it. So intermolecular forces, polarizability is another buzz phrase. And it's just based on the number of electrons in the electron cloud. So the bigger the particle or the bigger the molecule, the more electrons it has. When we think about LDF, London dispersion forces, those are all based on the random movement of electrons. So randomly, they could be hanging out here, right? When that happens, we have that dipole here. And the more electrons we have hanging out together, the stronger that dipole, the more polarizable the electron cloud. So that's really what we are looking at here. So when it comes to IMF, understanding not only what like constitutes each IMF, intermolecular force, also how do we decide the strength of each of these? So when it comes to LDF, it's the size of the molecule and the number of electrons. And then when it comes to like dipole-dipole interaction, it's the polarity. When it comes to hydrogen bonding, it's the number of sites, things like that. All right. So let's move forward. These are the equations that I recommend memorizing. These are the ones that are not on the equation sheet. A lot of these are just rearrangements, except for the first two. So the first two, the cell potential, let me make this bigger so you all can see it. The cell potential is equal to the cell potential at the cathode minus the anode. So I like to say the cathode comes first. The enthalpy of reaction, this is the one that frustrates me to no end, that it's not on the formula sheet. So the enthalpy of the reaction, you calculate entropy or enthalpy or Gibbs free energy, and it's always products minus reactants. As soon as you're looking at the bonds broken and the enthalpy of that reaction, it's the bonds broken, which are the reactants, minus the bonds formed. So just keep that in mind. The rest of these are pretty much just rearrangements. I just released a video on that, so you have access to all of those as well. All right. So things to know. This is going to answer quite a few of those questions that have been coming in too. You're going to assume the 5% rule always applies. I've had quite a few requests asking for some equilibrium practice with those rice tables. I definitely built some of that in for tonight. But just know that you can always ignore X. And we'll look at that in just a second. You don't even have to justify it on your FRQs. So we also are going to want to use 3 or 4 sig figs throughout. So basically, there is one hidden point for sig figs on the entire exam. You are not going to know where that is. It's going to be somewhere, and the readers will know, and that's it. Typically, it's going to be attached to some kind of measurement. My guess is that it's going to be something like reading a burette. Do you estimate that extra digit? Last year, it was on just a Q equals MC delta T question. And that was the one spot where you had to have the correct number of sig figs. So because of that, a single point. You are not going to waste time counting sig figs. You're just going to use 3 to 4 throughout. All right, I had a couple of questions come in. What is the 5% rule? So the 5% rule is just saying that if X is less than 5% of the initial concentration or the initial pressure, when we are setting up those equilibrium tables, we can ignore X from the initial concentration. I will show a practice problem with that, and that will make it a lot more, it'll make it just hopefully make a lot more sense. All right, so you want to check out the given units. If you are stuck, it's 9 times out of 10, you can just look at the units attached to whatever the question's asking for and work backwards. This is very true with enthalpy of reaction. A lot of students get confused with that. You're just looking for moles of whatever reactant. You already have the heat associated with that, and you're just dividing. You look at the units, it's it's kilojoules per mole of reaction. So you're dividing the kilojoules by the moles, right? You're using the units to your advantage. And then also, I want to encourage all of you, you're going to answer every single question because you're going to remember that error carries forward. What do I mean by that? That means that, no matter what errors you made in earlier portions of the question, as long as you are doing the rest of that question correctly, you still get full credit for that, even if you are using a wrong answer from an earlier subpart. Yeah. All right, and if your answer is off by a sig fig, would they mark it wrong? No, there's a tolerance of at least 1 sig fig. And like I said, sig figs, as long as you're not writing like 8 sig figs, you should be good. Yep. All right. Yeah, and if you've never heard of sig figs, I will just say, like, don't worry about it. Just seriously, don't worry about it. At this point, you're gonna be fine. All right. So, what not to say on these FRQs? We've talked a lot about like the buzz phrases and things like that, like things we should say. These are the things I do not want you to write. You can think them in your head if that helps you out. However, I do not want you to write them. So, the first one is like dissolves like. Like, I say like as I say that. Blah, right? What you want to do is you want to talk about what makes these two substances similar, right? A polar substance will dissolve in a polar substance because they have the shared dipole-dipole interactions. They are miscible, things like that. This idea that opposites attract, yeah, that's true. However, why does that happen, right? The partial positive and the partial negative, right? You're going to talk about the actual signs of each. And then based on the ionization energy trend, this atom is to the left of that one. Therefore, no, you're not going to ever do that. So these are just some of the things like the faux pas that your readers do not want to see on your FRQs. All right, this is just a little bit more about periodic trends. I promise I'm going to put all of that in there. Yeah, okay. So I'm seeing a lot of requests for buffers, acid base chem, all of that. All right, so what I'm going to do is I'm going to keep going through that. Yeah, here, let's answer this. I only have practice for FRQ, so let's talk about MCQs just briefly. I'd say a lot of students, and you guys call me out on this, like it in the chat right now if you feel this way. I think MCQs are harder than the FRQs a lot of times because these questions are just not very straightforward. And I think it's really easy to overcomplicate them. You're not the only one to feel this way. So my tips for MCQs are to, again, 3-pass system. Go through, answer all the easy ones, flag the hard ones, go back to them because you don't want to sit there spiraling for 5 minutes while you're trying to solve one of those difficult problems. And then because instantly your confidence just like drops. And then all of a sudden you get like an easy stoichiometry question. You're like, I can't do this. I can't do any of this, right? So you're going to go through, you're going to do all the easy questions first. Then you're going to go back. A lot of times as you answer the different questions, things will kind of click in and you're like, oh, wait, I know how to answer number 6 now. Like you can go back, it clicks right in. And if not, a lot of these questions, you can typically eliminate them down to like 2 out of the 4, right? You can get down to the point where it's a 50-50 shot. So you want to just make sure you're giving it your best shot. And if you want to go through and you still have like 6 or 7 questions left and you want to just put them all as C, that's fine. There's no penalty for guessing. So keep track of the time so that you have time to do that if needed. All right, so let's move on. So my plan was just to practice. So again, if you have not downloaded that practice, open up right underneath the video. You should see video notes, and that's where you'll have access to that. Yeah, and the plan was to go over Unit 8. I know everyone's still struggling with Unit 8 because everyone struggles with Unit 8 every single year. It is the hardest unit. And if you think about Gen Chem 2, so the class that you just took replaced 2 semesters of college level chemistry. While you are taking so many more classes, you have sports, you have so much going on, right? And a lot of times, like most of Gen Chem 2 is dedicated to acid-base chem. Most of you probably spent like, 2 weeks on this? Like, yeah, it is hard. It is hard. So let's look at these. So unfortunately, I wanted to like write this all out and like do this live with you all. And of course, I don't know how to stream well enough to do that. So instead, what we're going to do is we're going to talk through it. I want you to open up this doc if you haven't already. And what I'm going to do is I'm just going to talk through like how I would approach each of these. These are based on the questions that I expect you to see, this style question. So each of these questions, I just wrote this thinking of or looking at one of College Board's released FRQs so that these can be as realistic as possible for you all. All right, so I wanted to do kinetics because I've had a lot of DMs coming in just saying like, what do we do about kinetics? Like it's been so long since I've done this. What's going on here? So let's look at this question. So we are given experimental data. This is one style of the questions that we're going to see. And we want to determine the rate law of this reaction. So when it comes to rate laws, again, you have to think back. Rate law is looking at the concentration of those reactants in terms of forming the product. So we are only looking at the reactants here. So what you want to do is you want to look at a situation where each reactant is held constant so that we can then see how the rate changes. All right, so think about that. Look at our 3 trials. Figure out where you would identify where O3, ozone, is constant versus where NO is constant. and then go from there. So if we look at, I wish I had like a cursor on here. I don't even have a cursor on here. If anyone has suggestions for a better streaming site, let me know, because I'm so frustrated that I can't like annotate the screen for you all. So basically I look at trials 1 and 2 and I see that O3 is held constant, but my NO concentration is doubled. So now that I know when NO is doubled, my rate is also doubled, right? So what does that mean? That means that is first order with respect to the concentration of NO. Now in a situation where NO is held constant, trials 1 and 3, my O3 concentration is halved. However, my overall rate does not change. That means that this is going to be 0th order with respect to O3. That concentration of ozone does not actually impact the overall rate. So my rate law is just going to be rate equals K times the concentration of NO. So this would have an overall order of first order. All right, so now if I want to calculate the rate constant, I'm given all this data. Take your pick, do trial 1, 2, or 3, plug those numbers in and solve for K. The hardest part of this, I think, is actually remembering the units. So you can always actually write in the units and then figure them out that way. Or someone put this on one of my labs. I was like, why have I never thought about this? The units of K, it's molarity raised to the power of 1 minus the order times the inverse time. So I wrote time rather than seconds because sometimes it's seconds, sometimes it's hours, sometimes it's minutes. It just kind of depends. So when it comes to rate constant, I think it's pretty easy to find that rate constant, that lowercase k. However, the units are the tricky part. So that's just a little hack to help you remember how to calculate those units. All right, let's see. So that was just a little bit. I'm seeing a lot of requests for 7. And let's see, was there something else? 7, 8, and 9. Yeah, for sure. All right. So I was just going to go through this, and then what I'll do is I'll just start going through all of the other things. Like I said, I have like a slide deck that has content from every single unit. So we can go through any of that. And let's see. I think I had someone. Yeah, so I promise I've seen calculating resonance. We will look at resonance, but I do want to get through these FRQs first. So let's get through these FRQs so I can help everybody with the hard stuff, and then we'll go back and review resonance as well. All right, so question 2, I really think that we're going to be seeing some particle diagrams. When you see particle diagrams, I want you to take a breath, and I want you to just count. All right, you're just going to go back to the days of elementary school where you're just looking at patterns and counting things up. So looking at this, I have 2 H2 atoms, I have 2 N2 atoms, and I have 3, I should say molecules, not atoms. I have 1, 2, 3, 4, 5 molecules of NH3, right? So you're going to take a second and do that. Part A says if each particle in the diagram represents a partial pressure of 1 atmosphere, what is the value of Kp? So now I have to think, okay, Kp, another equilibrium constant, right? So that's the equilibrium constant in relation to pressure. So I'm just going to have the pressure of the products raised to the power of their exponents over the pressure of the reactants raised to the power of their exponents as well. So looking at this, I'm just plugging everything in, and then I have my answer. So Kp is 1.56. So with the previous question, right, we had to care a little bit about our units. So with rate constant, the lowercase k, we care about our units. With the equilibrium constant, remember, this is the one time in chemistry where you do not have to worry about units. So Kp in this case would just be 1.56. I'm going to go ahead and skip part B just because I have so many people asking about the next couple units, and then we'll keep moving forward. Let's see what else I have on here. Yeah, all right, buffers. Let's talk buffers because Unit 8 has been a hot request in here. All right. And I'm seeing a lot of students saying, okay, yeah, so a lot of people are having to self-study. I'm really sorry you're in that situation, but it is a hard class. It's just there's not enough time to get through the content. So if you are in a spot where you are self-studying, there are so many resources online. And please feel free to reach out too. I am always happy to send links or connect you with other people who are creating content for you all. My goal with these accounts is just to help as many students as I can. And I know there are lots of other creators out there who are trying to do the same. So if you are self-studying, know that you are not alone. We want to help you out. All right, buffers. So let's look at this one. So when you are doing acid-base chem, if you get stuck and you're like, I have no idea where to start, you're going to write a dissociation equation, right? So looking at this malic acid, what does this separate into? Well, it's an acid, right? So it's going to lose an H plus ion. That's where I'm going to start, right? So just recognizing, okay, then I'm going to be left with a conjugate base. When I lose that H plus, I just subtract one from the charge. Now I want you to get organized with this. Write down what you know. And in this case, we know the concentration of our weak acid, that reactant, and we know the concentration of our conjugate base. So now knowing that, okay, we also have our Ka value. How can we use that to find pH? Well, you have a couple options. If you want to, you can go ahead and write this out, right? You can figure out what your concentrations are going to be at equilibrium and go from there. Or you can remember that this is a buffer. So you are going to use the Henderson-Hasselbalch equation. It is on the back of your formula sheet, and it's really easy to use, right? So if you go to the equilibrium section, you'll see that pH is equal to the pKa plus the log of A minus over HA. So A minus is equivalent to the conjugate base. HA is the concentration of that weak acid. And know that with this equation, because these two species are in the same solution, you don't even have to do concentration, right? You can just do moles of that conjugate base over the moles of the weak acid, and that works out too. All right. So all I'm going to do is I'm going to plug that in. And yeah, someone said, okay, my problem would be finding the ratios, right? Like that is a tricky part. It's actually identifying like what everything is. So with this, your acid is what we're starting with. It's what loses a proton. The conjugate base is what the acid becomes after it loses that proton. So it's always the base over the acid in this case. So that gives us our answer here, and then we have our final pH. I have been rounding for sig figs. You don't have to though. And also when you look at the pH, remember that the pH, the sig figs are a little bit different. So it looks like I have 3 sig figs here. Really, I only had 2 because I guess I was lazy when I wrote this last night. But sig figs only start to the right of the decimal place. So because it's a logarithmic scale, that initial number just shows the scale. So just be careful. Yeah, don't say sorry. That's a great question. How do we know what's the acid and what's the base? So the acid is what loses an H plus. Typically, if you look at the reactant, it starts with an H. So that shows that this is what's going to be deprotonated, or it's going to lose that H plus. The base is what the acid, so in this case, this is a conjugate base. It's what the acid becomes. When you're looking at just like a regular acid-base reaction, right, the acid loses an H, the base gains it. So really, it's all about just looking at that moving H. Yeah, and where does the Na go again? So sodium is just a spectator ion. So I took it out so we could just focus on the movement of that proton. You can keep it in there if you want, or you can take it out. It doesn't matter. Spectator ions, they have to be we need them in solution, but they're not really important to what we're doing in terms of these calculations. All right. Yeah, so the Na, yes, that's a great question. So the Na, basically the sodium, monosodium malate concentration is equal to the conjugate base. Yes, that is the conjugate base's concentration. Yep, so a lot of questions there. Yeah. Can I go over net ionic equations? Sure. So net ionic, when we think about net ionic equations, couple different types of reactions that you're going to see net ionic with, right? So in a precipitation reaction, you're going to focus on the formation of the solid product and then kind of work backwards from that. With an acid-base reaction like this, we are looking at the formation of water. So always working backwards from that. With a strong acid, strong base reaction, that's just going to be H plus OH minus gives us H2O liquid. With a weak acid or weak base, it's a little bit different. So with that, you have to keep the weak acid intact because it only partially ionizes. So I'd have like HF plus my base gives me H2O plus that whatever that conjugate base is. It probably wasn't the best explanation, but I'll look and see. I should have slides that we can go over that with. All right. Yeah, all right. This is a good question too. How do we know what forms? Yeah, we'll talk about that. All right. So do we use moles in rice tables when they're different volumes? Yeah, so there are two different types of tables. So rice tables are where we use equilibrium concentrations or pressures. BCA tables are typically where we use moles. So in a buffer situation like this, I've combined these two solutions together, and that's why I can just use the moles there, right? So if I took the time to divide them by the volume of each, we'd still end up with the same ratio. So that's why I just use moles in this relationship because they're in the same solution. So it does not matter. Um, I don't know if that answered that question. Let's see. Yeah, will this live be available later? Yes, it will. And then what I do is I typically go through these these slides and I record just a video. So you don't have to deal with me like jumping in the chat and um kind of ADDing here as I look at all the different questions. Yeah, I like that. Someone just put something in the chat. How do you remember acids are yucky, bases are yummy? It tastes like they're having a meal with an H plus. That's pretty clever. I've never heard that. So what I say is acids just lose those protons, bases gain them. Bases get bigger. Yeah, and this is a great question. This ties into acid-base chem too. And this is a really common misconception for a lot of students. What's the difference between strong and weak acids and bases? And a lot of students will think, oh, like a strong acid has a really low pH and it's really dangerous. Not necessarily. So a strong acid is one that completely ionizes or separates in solution. So if I put hydrochloric acid in this volumetric flask, I wouldn't do that. I'd put it in a beaker. But I don't think I have a beaker anywhere that I can grab like this. So if I put HCl in here, it's all going to separate out into H plus and Cl minus ions. Versus if I take hydrofluoric acid, which is a very dangerous acid, only part of it's going to ionize or separate. Some of it's going to remain as HF, as that whole molecule. That's the difference between strong versus weak. So a strong acid, strong base 100% separates. A weak acid or weak base, it does not. We can determine that based on the percent ionization. Yeah. All right, let's see. Yes, and we will go over electrolysis. Happy to do that. Yeah, okay. So will they be using limiting reactants in buffer questions? So that would be one of the tougher questions that you might see. I would say that's like on the upper side of the hardest content that is covered in this course. So with this, like let's say you're finding the pH during a weak acid strong base titration and you're in that buffer zone. You're at a point where you have to see what's in excess in solution to be able to determine the pH. And I actually have a question where we will go through that. So yes, in a way, yes, you have to be able to look at that and make predictions. So with these acid-base reactions, it's always like a 1-to-1 ratio because we're losing one proton at a time. So rather than having to make a prediction about how much product each one's going to make, you can just see which one you have less of. Whichever reactant you have less of, that actually will be the limiting reactant. But don't don't rely on that in a normal reaction, right? Where you actually have to factor in stoichiometry and make predictions about the amount of product produced. All right, let's see. Yeah, I did say so I think we just answered this, but I did say BCA table. We'll go through that in just a second, I promise. When I do the acid-base titration question, we will absolutely do that. All right, I'm going to take my face off the screen so that you guys can see this. So this is problem number 4. This is another thing that I am predicting that you're going to see on this year's FRQ. So how do you all feel about Q versus KSP? So solubility product constant of barium sulfate is 1.10 times 10 to the minus 10th. So if I have a certain amount of sodium sulfate and I combine that with barium chloride, will a precipitate form? So what we're going to do is we're going to write the expression for the dissociation. I've already done that on the screen. But what you have to do is kind of like work backwards, right? So my solid precipitate is going to be BaSO4. I'm just separating that out into the respective ions. If you can't remember the charge of those polyatomic ions, you look at this, separate your cation versus your anion, right? The Ba is +2 because it's in that second column. That means SO4 has to be -2. Okay, so work backwards from that. You want to indicate the charge and the state in these dissociation equations or these net ionic reactions. All right, now we want to write the expression for the KSP or the solubility product constant. So K, again, we said K is equal to the concentration of products over reactants, raised to the power of the coefficients, right? So looking at that, what we want to do is we look at this reaction and we realize, oh, wait, like our reactant's a solid. Solids and liquids do not impact equilibrium, so they will not be included in those K expressions. So your KSP is just going to be the concentration of Ba2 plus times the concentration of the sulfate. That's it. So now comes the hard part. So now we want to use the solutions above to actually calculate QSP. To do that, I need to find the concentration of each ion. So we're going to remember molarity times volume equals moles. Long before I ever met my AP chemistry teacher, I remember him going through the hallway and saying, hey, yo, kid, remember, MV equals moles. And, sure enough, this many years later, I still remember it. This is something that's not on the formula sheet because it's just a rearrangement of the molarity equation, right? So the molarity is equal to the moles per liter of solution. So with this, what we need to do is we need to find the moles of each solution. Then we'll divide by the total volume to find the concentration of each. Once you have that, then you just plug it back into the KSP. It's the concentration of Ba2 plus times the concentration of SO42 minus. Multiply those two together and you have your answer. And that's what I'm going to show here. So again, like I said, I'm going to link all of this. I know we have such limited time. I will probably just record a video just going through this problem set too, so you have all of this. The last part is the hardest part, right? Comparing Q and K to predict. But this is something that you can also just memorize, right? So with this, we go back into the question stem. We see that K is significantly less than Q. What that means is when Q is greater than K, the reverse reaction or the formation of reactants is favored. And normally you'd be like, oh, so that means the precipitate's not formed. However, the precipitate in these reactions is your reactant. So if Q is greater than K, then the precipitate will form. Yeah. All right, let me see. I'm a little bit behind on the chat. Let's see. Yeah, so do we need to include states of matter? Yes, it is a good habit to include those. There are certain situations where you don't have to have them, but something like this, like a net ionic equation, you absolutely have to have those. The precipitation reaction. So I'd say, yes, include states of matter. Yeah, so a couple questions came in about that. Sorry. Yeah, why did I divide by the total volume? So my goal is I took two solutions, I mixed them together. So now my concentration of barium 2 plus in that new volume is going to be less than what it was originally. So that's why I had to find the moles of barium that I had from the first solution and then divide by the total volume. Yeah. Okay, let's see. Yeah, so Q and K are calculated in the same way, right? So why was K calculated rather than Q? Well, actually, Q and K are both. Oh, you know what? That's because I just made an error when I was trying to scramble and do this at 8 o'clock tonight. That should say QSP. Nice catch. So I calculated the QSP, but it's calculated in the same way as K, right? So Q is just at any time other than equilibrium. All right. Yeah, so if you got the wrong answer for Q, but you correctly justified, yeah, so let's say your Q was less than K, and you said, therefore, a precipitate would not be formed. You should get the point for that. Yep, just based on error carries forward. All right, I'm going to answer this. This is not related to what we're doing right this second, but what are my thoughts on the overall difficulty of the AP exam? I like to tell you all this because I know how stressed you are. I know you're really fixated on all the really, really difficult questions right now. Overall, I think the AP exam is not as hard as most of the questions that you've done in class. So for a lot of you, what you've been practicing with and what your teachers give you to prepare for this is a lot more difficult than what you might see. The questions are going to be written in new ways. They're going to be diagrams that you've never seen before. So how you think on your feet is going to be tested on Tuesday. But overall, I think, a lot of the basics are really what the test has been focusing on. And I really like how questions are broken up like this. So it's not just, okay, here's all of the information about the solution. Tell me whether precipitate forms. It's, okay, step by step. Here's what we need to get to that point. And I think that's really helpful. All right, let's move forward. Let's see. So moving on to electrochem, because I have had a lot of requests for electrochem. So this is just a standard electrochem question. We're going to go through just the balancing, calculating delta G, and then looking at Faraday's law, as well as just looking at the non-standard cell. Let's see. So take a second to look at this, and then we will move forward. I'm going to try to catch up with the chat really quickly. Okay. And of course, I'm seeing a bunch of questions from the previous one that I totally missed. I'm so sorry. How did I get that Q was greater than K? So K was given in the problem. So K would be given to you in a problem like that, or you would have calculated it earlier in the problem. Yeah, and if Q or K are equal, that means the reaction is at equilibrium. That's correct. Yeah, I mean, I was trying to hint at this, but I'm going to go ahead and put this one on the screen. I don't want you stressing out about AP Chem. I think a lot of you, what you have done all year long, you are going to be in a situation where you're going to sit down and hopefully it's just like a fun chance to show off what you know. So try not to stress. Definitely get some sleep between now and then. Focus on just, using this as an opportunity to show off what you've learned. All right, so Unit 9. So this does relate back to Unit 7 because we are going to be doing some more thermo with delta G. We are going to be looking at equilibrium constants, things like that. So you will see some overlap between Unit 7 and Units 9. So in this one, the balanced redox reaction. So whenever you see a table of values like this, know that those are reduction potentials only. So when we look at this, one of these is going to be the oxidation, one of those is going to be the reduction. So a redox reaction, right? It's a transfer of electrons. We are losing them from the oxidation is loss, right, of the electrons, and reduction is a gain. So with this, I'd look at this and immediately I'd look at that first reaction and say, wow, that's a really negative value. That indicates that is not a spontaneous reaction. I'm going to flip that one and add that to the other reaction. The goal is just to get those electrons to cancel out. And, tying back into some of the questions about how hard is this exam, I bet a bunch of you have had to balance redox reactions in acidic or basic solutions. You are not going to have to do that on Tuesday's exam. It is really just as straightforward as these types of equations. All right, so we're just multiplying everything by 3 so that our electrons cancel out. Then when we're calculating the cell potential, this is one of the equations that unfortunately is not on the formula sheet, so you need to know it. The cell potential at the cathode minus the cell potential at the anode is going to give you the overall cell potential or the voltage of that cell. So remember, the cathode comes first, and the cathode, also another mnemonic device to remember, is red cat and anox. So reduction happens at the cathode, oxidation happens at the anode. For part C, delta G equals negative NFE. You're going to look at the formula sheet. You have quite a few equations related to delta G. This is one we're looking for here. You have to remember N is equal to the moles of electrons. So you go back to that balanced reaction. We had 3 moles of electrons, and then you're just plugging everything in. F, if you have not seen that before, that is the Faraday's constant. It is on your formula sheet along with the units. Use those units because when you do a Faraday's law question with some stoichiometry, you're going to be using those units to figure out how to get from point A to point B. With these delta G and delta H types calculations, be careful with units. College Board likes to give everything to you in joules, and then you have to change it into kilojoules. Nice thing about any of the conversions you're going to have to do, right? It's just you divide by 1,000, and then you can quickly do that. So just be careful to make sure that your units match up with whatever the question's asking for. All right, let me see. I am so behind. I cannot keep up with the chat. You all are amazing. Hopefully this has been helpful. Yeah. All right. So another thing, just related to electrochem, and if you want, you can stay on and we'll keep going through some more stuff. Does the cathode gain weight or does the anode? So a lot of people will say, okay, the cat gets fat. So what that means is the cathode where the reduction is occurring is going to accumulate mass as the cell functions. That is true as long as it is not an inert or non-reactive electrode. So be careful with that. Yeah, and will the cathode be more positive? It depends. Are you looking at electrolytic or voltaic cells? So you have to be careful with that. So I think I saw another question in there. Are we going to know? Let's see. Yeah, so I don't see it, of course. Are we gonna know whether it's an electrolytic or voltaic cell? There are gonna be clues, or you're gonna be told. I will say it's been a few years since we've seen electrolytic cells, so I would think we might see one. In an electrolytic cell, you have to have an external power source for this to happen. So if we think about a voltaic cell at the anode, right, where oxidation is occurring, that's the loss of electrons. So that's the charge there versus when we are forcing it to happen, it's going to be flipped for electrolytic versus voltaic. All right. And this is relaying back to this question. You have to flip the one that is the negative voltage. So if you use the form of the equation that I just gave you, you do not have to flip any signs, but you do flip the reaction. So what we have to do is we have to have one that's a reduction, one that's an oxidation, which is why I had to flip that, so that instead of those electrons being a reactant, they're given off as a product. So yes, when you look at those two reactions, you are going to have to flip one because these reactions are always going to be given as reductions only. All right, and how did I know to flip the one that's super negative? You're going to look for the one that's not favorable, right? So a positive cell potential is the most favorable option. So looking at this, I see that negative 1.676. I'm like, that is not going to be an actual reduction. That has to be my oxidation. Yeah. All right, let's see. All right, so next up would be Faraday's law. This is another thing that I do expect us to see from Unit 9. Sorry. So in this situation, if an electric current of 10 amps passes through the same electrochemical cell that we were just looking for 30 minutes, determine the mass of silver deposited. This is where stoichiometry comes back. And what you're going to do is you're going to rely heavily on all of the equations and the units on the formula sheet. It's really nice that you guys have amperes in there now, and you see that that 1 amp is equal to 1 coulomb per second. So what I would do is I would start with 30 minutes. You know how to convert minutes into seconds. Then after that, I have 10 coulombs per second. Switch from seconds into coulombs. And then you look at coulombs, you're like, oh man, what am I going to do with that now? How am I going to get to the mass of silver? Well, think about Faraday's constant. That's 96,485 coulombs per mole of electrons. So you're just going through there, getting all those units to cancel out until you get to the desired units. Another style question you might see, you might be given the mass and asked to figure out the time the cell operates. So again, just rely heavily on getting those units to cancel out over the diagonal, using the constants and using your equation sheet to figure this out. Let's see. Yeah, so this is related to how much how much dimensional analysis in Stoic will there be on the test? So honestly, in the last couple of years, there have been like 2 or 3 questions where you just have to do basic unit conversions or Stoic, which is why a lot of teachers will say that you could do pretty well on the AP exam if like just having taken honors chem. So know that there will be some simple stuff on there too. But it's really important that you don't overthink it, right? You could see it and be like, I don't know what to do here. Do I use the ideal gas law? What am I doing? And like, it's literally like, no, you just need to take the mass and convert it into moles. So yeah, just know that you will see simple things like that. And that's okay. Look for those. Yeah. And how did I know that silver gained 3 electrons? So this stoichiometry here was based on the balanced equation. So going back here, for every 3 moles of electrons that we balanced out here, I created 3 moles of silver. So that's where that came from. I know. And those of you who have never taken Chem 1, I just like, I don't know. I'm in awe of you all because you guys are rocking it this year. There are a lot of you who have just jumped straight into AP Chem. But know that a lot of the stuff that you've been working through, like the stoichiometry, all of that, you will see it, and it is going to help you out. All right, so let's move on. So let's look at a non-standard cell. So if the concentration of Al3 plus increases from 1 molar to 1.5 molar, describe how the cell potential will change. So thinking about this one, what we need to do is the Nernst equation. So this is on the formula sheet. The good news is you're not actually going to have to plug all of these values in to solve for that non-standard cell potential. Instead, what you need to be able to do is understand how Q is going to change. So if I look at this, right, if I'm thinking about the relationship, so Q again is the concentration of products over reactants. In that balanced equation, I had Al3 plus over Ag plus because those were my only aqueous. Everything else was a solid. Those are my only aqueous substances. That's what those are going to define Q. So if the concentration of Al3 plus increases, my numerator increases, therefore Q increases. And when Q increases, according to that Nernst equation, my cell potential is going to decrease. So it's just a matter of like looking at if this changes, and there are going to be a lot of different questions like this where you're asked to make a prediction, like a student didn't let something dry long enough, like things like that. And you have to think, okay, step by step, how is this going to impact my calculation? So in this case, if the concentration of Al3 plus increases, Q is going to increase. When Q increases, I am subtracting a larger number from my cell potential. Therefore, the non-standard cell potential is going to be lower. Yeah. Yeah, and okay, how do we find past MCQs? The MCQs have not been released like the FRQs, but I know Mr. Faraday just released a 60 question MCQ test. So if you go to his page, you can find that. He has a podcast episode where he goes through all of the answers, but he also has that linked. So it's really good practice. His questions probably align best with what we see when College Board does release questions, or based on the questions that are released in AP Classroom. So as long as you've been doing test on AP Classroom all year, you've been looking at all of those released MCQs. If you are self-studying, keep practicing, keep doing what you're doing. I think someone said they were on Khan Academy. Khan Academy has great practice for you. Lots of different options, really straightforward practice. I do have the Princeton review book. I think it might be a little bit too late to pick this up now, unless you're taking the later exam on May 20th. But their questions are pretty straightforward too, if you're just looking for more practice with MCQs. All right, let's move forward because I know we want to definitely. Oh, okay. Yeah, Mr. Fairbow. Someone put it in the chat. He was actually my mentor teacher when I first decided I wanted to switch gears and become a teacher. So he has a lot of different practice available for you all, and I will say his stuff it aligns best with what we see. It just aligns best with what College Board writes. All right. I really haven't had many requests for thermo, so let me know in the chat if you want to go through this calorimetry question or not. And I'll put his name in the chat so you have it. All right, let's see. No, honestly, so Princeton Review, what I have seen from this is my first year actually like grabbing it. They have like a lot of content that's not necessarily covered by College Board. I wouldn't say it's like harder than the AP test though, necessarily. All right. Okay. We'll go through calorimetry. That's fine. That's fine. All right. So every single year we see calorimetry. And I think at this point, a lot of you have probably moved past that and you're like, I don't even remember how to do this. So let's go ahead and talk about that. So this one is a dissolution of calcium chloride. Right away, you hear dissolution, you're going to think, okay, I'm looking at the total mass now. So this is going to be Q equals MC delta T or Q equals MCAT, depending on what your teacher has taught you. And basically, we want to calculate the amount of heat released in the experiment. The fact that it is released, that tells us something too, right? So when the heat is released, that means that this is going to be an exothermic process. So we're going to have a negative Q in this case. So we want to assume the specific heat is the same as that of water. Again, another clue that we're going to be looking at the total mass. So we're going to add the mass of our solid to the mass of the water. A situation where we would not be doing that, where we'd have separate equations and we'd keep the mass separate. Let's say I have a piece of solid iron and I'm adding that to water and measuring the temperature change. There is no reaction between the water and the iron. Something like that, you're going to keep the masses separate. All right. So with this, all you know is Q equals MCAT. Yes, exactly. So Q is going to be equal to the mass, which is again going to be the mass of the water plus the solid times the specific heat of water, which we're given. We're given the units there, times the change in temperature. So change in temperature is always final temperature minus the initial. We do get a negative value there. That makes sense because again, we're looking at the heat released. So this is going to be 3,320 joules. And it really is just a matter of just multiplying the numbers together. And then calculate the value of delta H. This is something I talked about at the beginning of the live. A lot of students get tripped up on this. If you see the delta H of reaction, you're like, I don't know how to calculate that. Literally just look at the units there. We need the kilojoules per mole. We just calculated the joules, divide that by 1,000, and then divide that by your moles. And that will give you your answer there. So when you get stuck, when in doubt, look at the units and go from there. Yeah, how do I calculate enthalpy from Q? Um, so how do you calculate the enthalpy from Q? It's really going to be Q divided by the moles of whatever substance that is. So just look for that. We're just taking our mass, our 4.5 grams. College Board likes to give you the molar masses, which is really nice. So we just divide by the molar mass of calcium chloride, and then we have our answer. So Q over our moles will give us that enthalpy. Yeah, in number 8, why are we dividing? So what I did is when we calculated Q, that was in joules because our specific heat value was given in joules. So what I did initially is I calculated it in joules per mole. And then I looked at that and I said, oh, but the question's asking us for kilojoules per mole. So then I just divided by 1,000. Yep. Yeah. So yeah, you know what? See, that's my problem. I did this way too fast. You were totally right. That should be negative. It says indicate the sign, and then I didn't even do that. So I threw this together at 8 o'clock tonight when I realized I wouldn't be able to actually annotate the screen on this live stream platform. So what I will do is I will update that. Good catch. Look at you guys. That's awesome. So again, heat is released. This is an exothermic reaction. That would be a negative 82 kilojoules per mole. This is why when you take the test, you're going to take your time. You're not going to try to do the whole test in 10 minutes. Take your time and look back and make sure you're answering all of the question completely. Yeah, and where did I get the 0.0405 moles from? That came from the mass of calcium chloride. So the mass of calcium chloride was 4.5 grams. It has a molar mass of 110.98. So I just converted that into moles, and that's how I got that. Yeah. All right. So let's move on. Okay, this is kind of random. Do I think they'll ask about column chromatography? I do not. Typically, we see TLC, which is thin layer chromatography, knowing that chromatography is based on attraction. It's based on polarity, right? Is a substance attracted to the medium, the solvent, or the paper it's attached to, and then kind of seeing. Yes, you can think like dissolves like, right? Like something, a polar substance is going to move with a polar solvent, just things like that. Yeah. All right. Next up, IMF. So I did have a couple of requests come in. Let's talk IMF again. This is the standard style problem that we see. Something like this, you're given the structural diagrams. Honestly, you would probably get a lot more than this. You'd have all of your hydrogens drawn in and things like that. So comparing adrenaline and dopamine, we're given the boiling point of each. We're trying to justify why is the boiling point of adrenaline higher. So with this, what you want to do is you want to look for sites for hydrogen bonds. So we're looking for those hydrogen bond sites, already knowing that adrenaline is probably going to have an additional site, and that's what's happening here. So this has an additional site for hydrogen bonds. What that means is the stronger the IMFs, the higher the boiling point, right? Because the more interactions we have to disrupt in order for this to shift from the liquid into the gas phase. So that's what you're looking for here. Yeah, and why are we boiling adrenaline? I don't know, because I feel like we're just like yeah, that's a good point. I don't know. That's just what I came up with. So yeah, just doing a comparison like this. There also have been a lot of different things, a lot of different questions recently where they actually give you all the species, like the different substances. They give you the IMF that they experience, and then they say, okay, knowing that, why is the boiling point of this one higher than that one? So you look at everything that's been given. You're not identifying IMF or anything like that. You're just justifying, right? The stronger the intermolecular forces in general, the higher the boiling, the melting. The only exception is vapor pressure. So vapor pressure, the stronger the IMF, the lower the vapor pressure is going to be. Yeah, and dipole, okay, we can talk just briefly about all of it. So dipole interactions are interactions between polar species, and then London dispersion forces. Those are just everything experiences LDF because it's based on the random movement of electrons. So being able to label those and kind of explain, the relative strengths of those is very important. So the strongest IMF is going to be ion dipole forces, which is just the interaction between dissolved ions in a polar medium. So if I took salt and I dissolved that in water, the separation of that's going to be the strongest IMF. So it's just an interaction between ions and a polar solvent. Dipole interactions are between polar molecules. A stronger form of dipole interactions are going to be those hydrogen bonds. And then the weakest is going to be London dispersion forces. Yeah, and we can talk about hybridization and stuff. I know I saw some requests for resonance earlier. I can do that as well. All right, I do want to get to the acid-base stuff before. I know I've already been on longer than I said it would. So let's keep moving forward. Let's see. Yeah, this was just a gas question. I'm going to skip this just because I have not been hearing that in the, oh, okay, of course. And now I hear, let's talk gases. Okay, we can do a gas problem too. All right, this is the last official one on the problem set, and then I added some acid-base stuff. All right, so we have a sample of oxygen in a rigid container. So if you see rigid container, you know that you have a constant volume. We're pressurized to 1.2 atmospheres at 298 Kelvin. If the temperature is lowered to 80 Kelvin, determine the pressure of the oxygen. With something like this, you see a change in conditions. You're going to think combined gas law. It is given on the formula sheet right under gases, liquids, and solutions. So we're just going to think, okay, volume is constant. So it's going to be P1 over T1 equals P2 over T2. You're then solving for that pressure. Keep in mind your temperature always has to be in Kelvin. Thankfully, it's already given as that, but make sure to convert it from Celsius into Kelvin if you're using this relationship. So we're just solving for that to get our pressure. So that gives us, it does reduce the pressure, which makes sense. And then B, in terms of KMT, kinetic molecular theory, explain what happens to the gas molecules. You can tell I was rushing to get this on the screen before this live. So as the temperature decreases, the average kinetic energy of molecules also decreases. So what that means is we're having fewer particle collisions, and fewer particle collisions with the sides of the container means that we have a reduced pressure. So just understanding what's happening with those molecules. A lot of gas stuff is like straightforward and you can kind of like reason your way through it. It makes sense. So know that temperature actually measures the average kinetic energy of the particles. So if I have a high temperature, that means they are really moving. A low temperature, they are not moving. They don't have a lot of kinetic energy. So it all relates back to that. And then part C, I do think you're going to see some student predictions. I do think some of the students are going to be wrong. So that's why I included this on here. So when we predict the total pressure will be higher than the theoretical pressure, that's not true. So real gases are going to be lower because they actually experience intermolecular forces. So we think about KMT, we're thinking that, okay, ideal gases, no IMF, no particle volume, completely elastic collisions where there is no transfer of energy. None of these are actually really true, right? So when we think about that, a real gas, the pressure is going to be lower because we are going to have intermolecular forces holding these particles together so that they're not just completely moving randomly. All right. Yeah, okay. I've been getting so many questions about IMF and resonance. So I'm going to take a break from the problem set and we'll just talk about this. All right, on the exam for Lewis diagrams, are they asking for the best one or any? So in general, with Lewis diagrams, you want to obey the octet rule first. So the rule that everything wants to satisfy the octet rule, that is king. After that, then you're looking at formal charges. So you might be asked to calculate the formal charge, and you want to remember formal charge is equal to the valence minus the dots minus the sticks, which means it's going to be equal to the valence electrons minus the lone pairs on that atom minus the bonds to that atom. So with that, if you're looking for formal charges, we always want to minimize formal charge. We want our most electronegative atom to carry a negative charge if there's going to be one. And you want the overall molecule to match the overall charge of the molecule. So if it's a neutral molecule, you want to make sure everything adds up to 0. If it's a polyatomic ion, we want it to match that charge. Yeah, I don't know if that's... Yes, and I will definitely do the bonus question after that. And when it comes to resonance, I know someone was asking, explain resonance. So resonance structures. If we have a resonance structure, it's just one where the electrons are transferred. So we have different things. If you've learned any organic chemistry, you might have heard of an isomer. And you might see an isomer on there. So an isomer is just a structure where the actual geometry is different. You still have the same chemical formula, but how the atoms are bonded together might be different. So what you need to know really is resonance, which is where we are actually moving those electrons around in that molecule. The actual geometry, like how the order of the bonds, is the same. It's just, okay, do I have a double bond, a triple bond, a single bond, or lone pairs on this? And when it comes to resonance, like, I wouldn't spend a lot of time. You may have spent a lot of time in class looking at all different possible resonance structures. What College Board likes to have you do is look at 2 possible structures and justify which one is preferred. Or they're going to give you kind of like a skeleton for a Lewis structure and ask you to fill in the most likely structure, something like that. Yeah. Yeah, sorry. I didn't mean to scare anyone with orgo for a second. All right, let's move into the bonus question. I put this one on here because this is what all of my DMs are right now. So let's just talk some acid-base chem. And I will also let you know, I know I've been on here for almost an hour and a half. I'm sorry it's been so long. But what I'm going to do is I will post at least this. I'll probably go through this. I'm going to post all the video notes so you have access to all of these. And then I'm also going to just go through the problem sets and actually work them out on my tablet so you can see how all of this comes together. So that's the plan. I know we have very limited time. I know you're feeling that crunch too. And okay. All right. Do I have an easy way to memorize all of these shapes? I do not. I have a note sheet. I have linked that. I can link that as well if you'd like it. But at this point, my vote is you shouldn't memorize it. It's not worth the time to memorize that for maybe 1 or 2 points. Last year, we saw tetrahedral geometry too. It was a very simple. It wasn't anything with the expanded octet. Do you really need to know what square planar looks like? I mean, you could see it potentially. Is it worth memorizing it right now? No, it is not. All right, so let's talk acid-base chem. Yep, so that's what we're going to do right now. Let's do some 8 and 9 review. So acid-base chem, this is the hardest stuff in the curriculum. Yeah, exactly. So salicylic acid, it's a weak acid. So right away, you know it's weak. So you know that we're going to have to do Ka and everything. So we want to write the acid dissociation expression for this weak acid. So I'm just going to look at the chemical formula. I'm going to subtract an H. And then when I do that, I'm going to have the negative conjugate base as well. So knowing how to just do this, that's a point. Now, if the Ka of 0.2 molar salicylic acid is 1 times 10 to the minus 5th, determine the pH of the weak acid. So then what I want to remember is that Ka is equal to the H plus times the A minus over that initial concentration of HA. So really Ka for all of these weak acid dissociations is always going to be X squared over that initial concentration because again, the 5% rule always applies. So what we are going to do is we're going to look at this and we're going to solve for that X value. So let me go back. See, this is why I'm going to actually work all of these out so you have these as well. So when we have H plus times A minus over HA, so basically I'm going to end up with X squared over 0.2 is equal to 1 times 10 to the minus 5th. From there, then I can solve for X, which is going to be my H plus concentration, plug that back into my pH equation to get a pH of 2.851. I do have what looks like 4 sig figs. This is actually only 3 sig figs because, again, that first number does not count towards sig figs. All right, so that's the easier stuff. Then we get into the acid-base titrations. So now I'm taking that salicylic acid and I'm titrating that with KOH, which KOH, group 1 ion, that is a strong base. So because of that, we are now titrating a weak acid with a strong base. You could see something like this. You could see a weak base with a strong acid, or strong acid, strong base. You should not see a weak acid, weak base on this test. So what we want to do with this, thankfully it's going to be split up. Don't get overwhelmed. You can do part C, and then we'll talk through how we do parts D and E as well. So we want to determine the volume of 0.5 molar potassium hydroxide needed to reach that equivalence point. We need our chemical formula first. So what I wish I had things. I wish I could just write on the screen. This is so frustrating. So basically, what we need to do is we need our chemical equation. We need our KOH plus the salicylic acid gives us H2O and then our conjugate base. So we're going to do that. We're going to set that up. It is 1-to-1. So we find our moles of acid first, which is just going to be 0.2 times 0.03, because you're going to remember MV equals moles. That's going to give us 0.006 moles of that acid. At the equivalence point, what's true? Moles of acid are equal to moles of base. So then I divide by that concentration to find my volume needed to reach that equivalence point. And I find out it's 12 milliliters. So then part D, I look at that and I think, oh, 6 milliliters. That is half of the equivalence point. What happens at the half equivalence point? At the half equivalence point, I'm going to give someone a shout out because they put this in the chat. At the half equivalence point, you have to remember the pH is equal to the pKa. You are absolutely going to see this on the FRQ, and you're going to see this and you're going to be like, okay, easy point. You're going to look at the graph. You're going to remember this. You don't have to do any kind of calculation because you remember this. So at that point, I'm just going to take the negative log of the Ka value to find my answer to part D. All right, so let me show you the answers to this. So you have that. Let's see. Yeah, so that's all we need to do for that. Like I said, I'm going to record a full video so you can see this actually worked out just in the style of my regular tutorial. Yeah, I feel like maybe I should have just hosted a live at the whiteboard. Just easier sometimes. All right, so yes, and everyone's remembering it. You're going to remember that. And if I have a weak base, right, POH is equal to the PKB. You can quickly do that conversion back and forth and you'll be fine. All right, so now comes the hard part, right? In part E, what I want to do is determine the pH at the equivalence point. And I have all the work on the screen, unfortunately, but I'm going to walk you through it. So let's talk through this. So basically what we have to do is we have to have our acid dissociation equation. And earlier we were talking about BCA versus those Rice tables. When I am working with moles, I use a before, change, and after table. It does not necessarily matter if you label it as Rice or BCA. This is just one of those little things. I like to do this so I keep track in my head. I'm working with moles right now. So I have the moles of acid, I have the moles of base. What's going to happen here, right? This is where we also have a little bit that stoichiometry and limiting reactants. So because this is the equivalence point, they are equal. So we're not going to have any acid or base left over. What we are going to have left over, though, is that conjugate base. And that's what the pH is going to be based on. So I'm going to take my moles of that base, 0.006 moles of the C7H5O3 minus, and then I'm going to roll into step 2. So I need to find the concentration of the conjugate base. Once I have that, I can then set that equal to my Kb. In this case, I was only given a Ka. So what I would do is I take the Kw, which it's given to you on your formula sheet as 1 times 10 to the minus 14th. I divide that by my Ka to get my Kb. My Kb expression, right, is the concentration of OH minus times that, you just set that up in the same way we set up Ka. So that's going to be x squared over that initial concentration. Solve for x. X is your hydroxide concentration. Plug that back in, get your pOH, and then remember, 14 minus pOH gives you your pH. Yeah. How did I get, okay. All right, so how did I get that 0.006 moles to start? So I was given the initial concentration and the volume of the acid. Remember, molarity times volume in liters is going to give you the moles. So I had the moles of that at the equivalence point. I know my moles of acid and base are equal. That's how I knew where to start. Yeah, so let's see. So in equilibrium, so this is at the equivalence point of a titration. So the equivalence point by definition is where the moles of acid and base are equal. Yep. All right, let's see. Yeah. Let's see if I missed anything. Yes, and this is a good point. And someone else also mentioned this, so I'll give you a shout out too. So for part C, you could have just used M1V1 equals M2V2. Let me show you that part as well. So when we were finding the volume, it is a 1-to-1 ratio, so technically we could use that. I tend to show it in this way because that's not always true, right? If we have a situation, let's say I had instead calcium hydroxide, right? Then it would be a 2-to-1 ratio of base to acid, and we'd have to do some stoichiometry there. So it's best to find the moles of one and then solve for the concentration of the volume from there. But yes, technically we totally could just do M1V1, or molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. All right, and where did the K go in KOH? I took the spectator ions out of that just to clean things up. You could have included KOH here, and then you'd also have the K with that final product. All right, let's see. Yeah, and how did I get the 0.042 liters? Let's go back to that part. So here I did jump around with this. So what I had to do is I had to look at the total volume of the solution. So initially we had 30 milliliters of our weak acid, and then we had 12 milliliters of our base to get to the equivalence point. So adding that together, that gave me the 42 milliliters. That's where that came from. Yeah. And if it's a half equivalence, wouldn't just times 2 give you the pH? Yeah, let's talk about why that's not the case. So when I think about the half equivalence point, that's where I have neutralized half of my weak acid. So my weak acid and the conjugate base concentrations are equal. So the pH is not going to be half of the pH at the equivalence point. The volume is half, but the pH is not. Yep. And how do I intuitively know which were going to be spectator ions? Because you're going to remember Na and K are always aqueous. So when it comes to solubility, I just posted a video on like what to memorize for this course. Solubility rules. You want to memorize what's always soluble, what's always aqueous. So sodium, potassium, nitrate, acetate, ammonium. Those are the things that are always going to be AQ. Those are always spectator ions. That's a great question. Yeah. Let's see. No, you would not have to use you will not have to know the formula of this. They will give you all of the formulas. I think I just had erased it. It was given to you earlier in the problem. That was my fault. Yeah. So it'll always be given to you. A lot of times College Board's even gonna give you the molar masses, which is really nice. You will not have to use 0. There's a 0 chance that you actually have to use the quadratic formula. You can always assume the 5% rule applies. You don't even have to justify it or show. You just immediately negate x. Why is kW x squared? Yeah, so Ka or Kb, those acid and base dissociation constants, they are going to be equal to x squared over that initial concentration, just because it's a 1-to-1 relationship between those two ions that they're dissociating into. And for part B, how did I get the Ka? I think it was given in the problem. Let's see. Let's go back. A lot of times it's given. Yeah. So Ka is given. So then I can set this up equal to that to solve for x, which is my H plus concentration, and then go from there. Yep. And this was also 0.06. Yeah, 0.006. So they're both equal at the equivalence point, and that's how we can go through all of that. All right, sorry, I'm trying to... Yeah, and now let's talk about E. So part E. So now a student uses 1 molar instead of 0.5 molar potassium hydroxide. So right away, I'm thinking through this. I'm thinking, okay, I've doubled my concentration. So that means I'm going to have half of the volume to get to the equivalence point. She predicts that this will decrease the volume, but will not impact the pH. Do you agree or disagree with her prediction? Justify your answer. So I will say I wrote this earlier tonight, and then I realized this is probably a little bit above the level that you would be expected to answer, but we could talk about it, right? So basically, you think about this at the equivalence point, the moles of acid and moles of base are equal, right? So how is this going to change? We have half the volume, which means when I'm calculating the concentration of that conjugate base, right, the volume is going to be less. So that means it's going to be more concentrated. So if I have a stronger conjugate base, my pH is actually going to be a little bit higher. It's going to be really small, and I calculated it just so I could justify this. So originally it was 9.076. With this change, it would be 9.111 at the equivalence point. So being able to take a question like this and think, okay, how is this going to influence my calculation? Just take it step by step. So my concentration increased, therefore my volume was reduced by half, which means that my concentration of conjugate base will be higher. Because that concentration is higher, my overall pH will also end up being higher. Just something like that. So just being able to go one by one and figuring that out. Hopefully that was enough of an answer. Yeah, no. CH4 is methane. But you would be given that. So on the test, every single time they give you a formula, they're going to say, okay, methane, parentheses, CH4, molar mass, 16 grams per mole. They give you a lot. They're going to give you a lot of the reactions that are going to be balanced, things like that. Hopefully you're going to be surprised by that. Yes, and I will post this. I will post this later. I will also probably go through and just actually do a very quick video where I'm not jumping around in the chat as much. So if you prefer to just watch a very straightforward video, I will also include that. I know no one has enough time these days. I know you guys definitely don't. So I like to try to make sure that all my videos are as succinct as possible. Yeah, this is a great way to remember solubility, right? Spectator ions, sodium, nitrate, ammonium, and potassium. Great way. I like to include acetate in there, which is C2H3O2 minus, but yeah. Yeah, why are there 0 moles of the acid left in this question? So when we get to the equivalence point, by definition, the moles of acid and the moles of base have neutralized each other. So to find the pH at the equivalence point, that's why it's based on the conjugate base that's in solution, because we are always looking for what is in excess right now. That's what's going to change. That's what's going to determine our pH. Yep, and Kw is given on the sheet. It is 1 times 10 to the minus 14th at 25 degrees. In a neutralization reaction, is the net ionic equation focused on the water? Yes, it is. So if I'm looking at a strong acid, strong base equation, I have a fly now landing on me. If I'm looking at that, then I'm going to work backwards from water, right? So water is just going to be H plus OH minus. That gives me liquid water. That's my net ionic equation. If I have a weak species like HF, I'm going to keep that weak species intact. So I'd have HF plus OH minus gives me H2O plus F minus. Same with a weak base. So that's the difference there when it comes to net ionic equations. Let's see. I'm not sure if I understand this question. So is it correct to assume that in a question like this, any substance that has a listed number of moles will always go to 0 in equilibrium? So remember, we are looking at the equivalence point. It's a little bit different from equilibrium. So at the equivalence point, we have neutralized the moles of acid and base. That's what we're focusing on here. So in this case, we did subtract. We are at the equivalence point, which by definition is where the moles of acid and base are equal. That's why both of those are 0. If you think about all the other points in a titration, right, the pH is going to be based on what's in excess at any one moment. All of these reactions are going to be a one-to-one reaction. So you're looking at which one we have less of in terms of the reactants. That's your limiting reactant in this case. For everything else you do in chemistry, right, you have to make a prediction about how much product each one makes. But because these are all one-to-one, look for the one that we have less of. Then subtract that from all of the other quantities, add to the products, and then go from there. Yeah. Yeah. How did I know that the conjugate base was the Ka? So with this, I was looking at my conjugate base because that's what was left over in excess. So when I have a weak acid plus a strong base titration, the way I measure that pH at the equivalence point is based on the excess conjugate base. If I had a weak base, strong acid titration, I'd be looking at the excess conjugate acid at that point. If I'm looking at other points of the titration, though, let's say I'm in the buffer region, right, where I have more of my weak acid compared to my conjugate base, right? It all depends on what is in excess in that solution. If I move past the equivalence point, then I'm just looking at the excess hydroxide, things like that. Yeah, and snap ions are always soluble. Yes, that's correct. No, and you don't need to memorize salicylic acid or anything like that, or the quadratic formula. Um, yes, you do need to know the strong acids, though. Some teachers will say 6, some will say 7 and add HClO3 in there. But yes, you absolutely need to know strong acids. College Board tends to use the same ones over and over again, so we see HCl, HBr, and HNO3. What you definitely need to know, though, is that HF is weak, so be careful with that too. Yeah, so what I'm gonna do is I'm gonna post all of my notes in the meeting, so you have this as well, but I think I'm gonna be hopping off before I lose my voice so I can record some more content for you all. Um, so thank you all for being here. I will say, let's see, I have so many slides. So basically what when I attach the video notes, you're gonna see just content from the entire course so that you have it. As you can see here, like this is all just unit 9. So what I want you to remember at this point, we are less than 48 hours out. You really need to focus on taking care of yourself between now and then, right? Like get off tonight, get some sleep. On Monday, make sure Blue Book is working, make sure your calculator is ready, you have your pen and your pencil ready ahead of time. Don't skip breakfast. Like this is a hard exam. This is a long exam. Take time, get to your site early. You can laugh or cry with everyone else testing, and then as long as you don't have a double on Tuesday, plan on going and doing something to celebrate, whether that's getting um, guacamole together or going to get ice cream, doing something. Like you deserve to celebrate being done with this course. So I want you to keep that in mind and just know you are so close to the end. And after you take this test, you're not thinking about it again until your score comes out in July. And when it does, I still want you to be proud of all the time that you have put into this course. Like it's amazing what you all have learned. So many of you have jumped straight from bio to AP Chem without even having taken honors chem, right? Think about how you felt at the beginning of the year when stoichiometry was the hardest thing you had ever done. And now you're looking at it, you're like, stoic, like I want to see stoic on this test. Like stoichiometry would be great. You have learned so much, and Tuesday's just going to be your chance to show it off. So I will continue posting stuff. I'm going to put all of the notes on there. And you guys are going to rock this and come back. I will, as soon as it's released on Thursday, I'm like giddy about it. I like print it out, sit down and take it, and I will post like, what do? I do this every year and I can't even think of it. I will make fun of the exam, and I will also post my predicted answer key so you have it. So again, like I said, when you are done with it, I want you to just brush it off, right? Move forward, get ready for all of the other 7,000 AP exams you have in the coming 2 weeks, and just be proud that you were one of the few who survived AP.